Hello and welcome to this complimentary webinar with the title Omics Skin in SIMCA 14.1. My name is Lennart Eriksson and I'm part of the data analytics business within Sartorius Stedim. The roots of our business go all the way back to 1987 when Professors Svante Wold and Rolf Karlsson formed a company in northern Sweden, initially called Umetrics, which later became Umetrics, and these days Sartorius Stedim Data Analytics. And today we are fortunate to have Professor Johan Trygg on board to continue to drive our innovative efforts. Our mission is driving growth by enabling our customers to see what others don't, and our vision is to be recognized as the leading data analytics solution provider. We are a business solution provider within the fields of advanced data analytics, and our solutions are realized through the so-called Umetrics Suite. The Umetrics Suite has a number of software elements inside it. We have, first of all, the MODE software for design of experiments to get all data right from the start. We have the easy analytics solution to enable everyday data-driven decisions in an efficient manner. Then we have the flagship SIMCA for multivariate data analysis, and this is also where today's presentation will take place. Beyond the SIMCA for offline data analysis, we have a couple of online extensions. We have SIMCA Online, Control Advisor, and Active Dashboard in order to make all the output from SIMCA, the SIMCA offline solution, to become accessible and useful in a very optimal way. Today we're going to talk about one of the specific user interfaces that comes with the SIMCA software, the so-called Omics Skin. Here we have an outline of today's presentation. First of all, we're going to dwell a moment on why we have developed an Omics Skin, who we think are the intended users. We will then become familiar with or familiarize ourselves with the Omics Skin. What does it look like? At the heart of the Omics Skin, we have an analysis wizard. The analysis wizard can be seen or understood as a guided workflow, and the guided workflow will guide the users towards accomplishing two types of data analytics models. And the first model is the so-called principal component analysis model, PCA for short. The second model is an OP-less discriminant analysis model, or OP-less-DA for short. We are going to demonstrate the analysis wizard in great detail throughout the software demo, but we will also demonstrate additional tools outside the analysis wizard that can also be easily accessed inside the Omics Skin. There will also be some conclusions and Q&A towards the end. So why have we then developed an Omics Skin? Well, the reason is that we want to simplify the use of the SIMCA software and make tools for omics data analysis more easily and more readily available to people that have an interest in analyzing omics data. And the hallmarks that we have been taking into account when developing this skin are that the skin should be quick, easy, and reliable. Quick in the sense that this skin is a customized SIMCA interface, whereby it is possible for us to concentrate all the important tools in one place, and thereby enabling an easier access to omics related features. Easy in the sense that because of one of the main ingredients or one of the main elements of the Omics Skin is a so-called analysis wizard. And this analysis wizard can be used as a guide. It represents a workflow guiding the inexperienced user all the way from import over to a report of the most interesting findings. And when developing this analysis wizard, we have also done that with the vision that the user should not necessarily have to know a lot about multivariate data analysis. So no detailed MVDA knowledge is required before you can start to use the analysis wizard and the Omics Skin. And reliable in the sense that the Omics Skin is using or is based on SIMCA's well-established and recognized technology. all the tools that are available inside the mainframe SIMCA are also accessible in terms of the Omics skin. And reliability also comes with the fact that within the analysis wizard we have several steps where we are going to clearly state or list if a model is reliable or not. So who are then the intended users? Well, of course, this will be scientists, engineers, and technicians working in industrial and academic sectors touching upon omics-related questions. This can be pharma, food, anti-doping, agriculture, and so on and so forth. And we see in front of us that the typical user might be a biologist or an analytical chemist, but of course many other industrial professions may also come into play. The common and uniting theme for these people is that they are used to working with complex instruments and that they also trust the results and output arising from these instruments. And the value that these users are expecting or seeing in front of them is, in addition to a reliable analysis of their data, of course, that there will be some short list of potential biomarkers or discriminating variables separating the groups of samples that they are currently analyzing. And as I said, it is not a must that the user is familiar with MVDA. So with a minimum of training, the user can turn their dataset into a list of discriminating variables that will help them in their future quest towards understanding what is discriminating, let's say, a reference group from a treatment group. So SIMCA comes with 3 different skins, and you can change between the skins under the View tab, the skins group. The default skin is the one that you normally see. We have an Omics skin that is targeted in this presentation, and we also have a spectroscopy skin that is there to help users of multivariate calibration to have a quick and smooth use of the SIMCA software. So regardless of which skin you are using, you will, with a click, change the interface, the different tools and default settings. And on this slide, we are zooming in on what the Omics skin looks like. The Omics skin, like all the other skins in the SIMCA software, contains a series of customized ribbons. And on this slide, we see in detail what the Home tab of the Omics skin looks like. We can see that we have concentrated the most frequently used tools for omics data analysis in one single place inside the SIMCA software, thereby enabling a very swift and smooth access to all these tools. And for an omics data analytics person that has some experience in multivariate data analysis and also is using SIMCA on a frequent basis, actually the Home tab represents a guided workflow all the way from importing data, going over the dataset button where you can, or the dataset group where you can view the imported data as tables or as plots, over to the work set where you're defining which subset of the data you're going to calculate your models on, where you're calculating the models, where you're plotting the model parameters and interpreting the model, refining the model if necessary, all the way over to the validation stage where you're validating the relevance of your model, and finally to the report where you will be reporting all your and documenting all your findings. For a person that is perhaps less familiar with omics data analysis and the SIMCA software, the Omics skin also comes with an analysis wizard by which you have a very guided workflow towards a very specific problem, the two-group comparison problem. And if you're launching this analysis wizard, you also have a guide from dataset to report. And this is what we will be targeting in the next couple of slides and also the software demo. So once you have launched the analysis wizard, this is the first view you will see where you're defining the work set. Before going into the details, I also want to emphasize that this analysis wizard that we're looking at, there are also other analysis wizards, but the one that we're currently targeting is only available in the Omics skin. So you have to have the Omics skin, first of all, installed, and secondly, enabled before you can see this view. So the first step is one of workset definition. So you're going to have to tell the SIMCA software what type of data you are importing. There are 5 predetermined types of data that SIMCA will understand: mass spectrometry data, NMR data, chromatographic data, the situation of identified metabolites, and the general situation. And when you have identified the type of data you're going to import, with that comes also a predetermined understanding of which scaling is appropriate. Of course, you can always overrule the initial guess made by the SIMCA software as far as the scaling is concerned, and all kind of scaling and centering options that are available inside the mainframe SIMCA will also be available when clicking this scaling line here. The next thing you have to specify is what you want to accomplish with the data analysis, i.e. you have to define the objective. And there are 2 data analytics objectives that are more common than the others, and that is the raw data analysis, where you will perform principal component analysis to overview the data. And the second one is the 2-group comparison, where you will be basing your analysis on the OPLS discriminant and data analytical engine. There is also a functionality by which you can very quickly and simply define groups of samples, provided that you during the import, and we will demonstrate this in the software demonstration part, have an identifier or understand that as a label or name of the different samples that you can designate as a group ID. It will be very quickly to define groups inside this analysis wizard. The nomenclature used in this wizard is that we will have a reference group, and the reference group holds the normal configuration samples. This can be a wild type, it can be a reference group where you have control samples, it can also be healthy samples or untreated samples. And then we have what we call group 1. The group 1 is the group of samples where something have happened. It could be the treatment group, it can be a genetically modified group, it can be a group of individuals undergoing some sort of exposure to a treatment with a chemical or a drug, or it can be a group of samples representing some sort of disease state or some sort of syndrome. Then when you click next in the analysis wizard, you arrive at the stage where you are going to perform the first of the 2 models, and this is the principal component analysis models. And those of you that have attending other webinars or watched other recordings in our series of recorded complementary webinars will recognize that the objective of the principal component analysis solution is to give an overview of your data, to identify groups of samples. If you're measuring data with time, to expose trends with time, and also look for samples and or observations that are deviating for some reason. We would call those deviating samples outliers. So with the PCA model, you will have 2 primary plots as outputs that are tiled side by side. It is one plot that gives an observation overview to the left, and then there is a plot called distance to the model to the right. And the distance to the model plot summarizes the deviations for each individual sample or observation. And we can then identify outliers samples in both plots, and we can also highlight samples in one plot, and it will then be automatically highlighted in the other plot. And when we highlight these samples, we can also use a complementary tool to try to interpret the deviations, and we will see how you interpret such deviations very shortly. But if you do not know in the beginning when you're importing your data set, if there are groupings in your data, you can at this stage actually mark observations and assign them to a class, and you can also correct an incorrect class assignment here. So this is the whole purpose of the first model, to overview your data, to see if there are structures, groups, and outliers, and if possible or if necessary, perhaps you can both exclude samples from the model that are too strongly deviating, and you can also reassign class membership if you for some reason suspect that your initial class assignment was not the correct one. And above all, if you have no clue whatsoever upon importing your data what sort of subdivisions of samples you have in your data, you can actually assign samples to non-defined classes at this stage. When you click next, you will then move over to a stage where you can start to interpret deviators, and we will discuss this possibility based on the highlighted sample here that is slightly deviating outside the model border. So the tool we are then creating upon clicking the red sample in the previous screenshot is called a contribution plot. And the contribution plot is very simple to interpret. For every variable that you have in your model, or every column you have in your data table, you will get one bar. And the larger the numerical value is for this bar, the more strongly this sample is deviating in the variable that is highlighted. A positive bar, like for this variable, means that the deviating sample has a larger numerical value than the average sample, and the negative bar means that the variable in question have a smaller numerical value for this sample compared with the group average. So this means that the contribution plot will show us which variable that differ, and the contribution plot can be implemented in different modes. You can compare a group with a group, but you can also compare a group with one point, and you can compare 2 points with each other. And if you think that a certain deviation is too large or too difficult to explain, you can also exclude those observations or rows in your data table using the exclude tool to update your data set with more representative and relevant data before moving over to the second data analytics models, which is where you're really targeting why the two groups differ. So the second model, or the second main stage in the analysis wizard, is what we call the OPLS discriminant analysis model. The initial view for this model is similar to the PCA model, which means that you have what we call a score plot and a demon X plot tiled side by side. But you're still going to have to look for deviating samples and outliers, because outliers in the initial PCA model may be different from the outliers in the OPLS discriminant analysis model. So there can be outliers in the initial PCA model which are not necessarily showing up as outliers in the second OPLS discriminant analysis model. And if you then find some deviator or outlier in either the score plot or the demon X plot, you can interpret those deviators using a contribution plot, which is very similar to the contribution plot we just looked at. In addition, for the OPLS discriminant analysis model, we also have a model quality guide in the lower left-hand part of this window. This model quality guide summarizes a lot of the most essential model performance indicators, and it also provides statistics from some of the complementary tools that are running in the background behind the scene and are not part of all the plots and tool sets that are seen in the analysis wizard. And in this case, the model is statistically good. The p-value is below 0.05. And when we are then clicking next, if we feel that this model is good and we would like to proceed, we're going to come to a stage where we are looking at one of the most central plots in the OP-less discriminant analysis model, and that is the so-called S-plot. We are temporarily now leaving the wizard just because I would like to provide some more detailed information about the S-plot, how to use it, what it represents, and how to interpret it. So the S-plot is given that name because very often when you're plotting the variables, they will, for an OP-less discriminant analysis model, they will pattern the letter S. So the S-plot comes from a plot where you're plotting the normal predictive loading of the OP-less DA model versus a correlation scaled version of the same loading. So the x-axis or the horizontal axis where we are plotting the normal loading will show us variables that have a strong influence on the group separation. This is because the loading that we are plotting is based on the covariance between the x variables and the predictive score vector t. And together with that information, we're then providing the correlation scaled version of this first loading of the predictive component. And this correlation scaling means that the y-axis will actually represent the reliability of each x variable for accomplishing the group separation. And that information is possible to extract because the correlation scale loading will be witnessing about the correlation, not the covariance, but the correlation between the original x variables and the predictive score vector T1. And we can also see that because we are correlation scaling the loading P1, the numerical range will be between -1 and +1. Without digging too much into the details, we can say that in very many cases, the loading points being part of this S-plot will, as I said, define an S shape, thereby the name. And when we have that sort of situation, we can distinguish the group discriminating variables from variables that have no discriminatory power whatsoever. And in this example, there are a couple of variables that are marked by the blue color. These are variables or chemical shift region integrals or mass spec MZ variables that increase numerically when we go from the control group to the treated group. So they have a higher value in the treatment class or treatment samples compared with the reference or baseline group. Conversely, we have a set of red variables that have the opposed change. It means that they are decreasing numerically when we're going from the control group to the treated group, or they are decreasing numerically going from the reference group to group 1 using the notation of the analysis wizard of the omics skin. And we can then continue with those highlighted variables for a more detailed analysis. And how to do that we will also look into in the omics skin demo. So as I said, we can investigate a single variable that we find having a discriminatory variable power just by clicking on it. And when we are clicking on an individual variable, we are going to replace the right-hand part of this screen with the dot plot. A dot plot is conceptually very similar to a histogram plot, but it shows each observation as a unit, as a circle. So the observations are, like with a histogram, sorted into bins representing variable sub-ranges. And for a perfect discriminator, you would expect a green color in some of the bins and then a blue color in other bins. So the variable that we are highlighting for the moment do not have the perfect ideal discriminatory power, but it still has some discriminatory power between the samples that are making up the two groups in this example. And we will, when we move over to the SIMCA software, also provide you much more detailed information about the plots of this example. So this brings us over to the software demo, and we will be using a dataset containing two classes that is drawn from our compilation of tutorial exercises.
So the first step is to import data, and we're going to import some GCMS data that I will explain in a moment. We will just locate the file, we open the data, and we will tell what is data and what is identifiers. So SIMCA works with identifiers, and you need at least a primary identifier for the rows and a primary identifier for the columns. You can have then optionally many different secondary identifiers, and identifiers are then used to emphasize certain things in doing the plots. It can be information that you would like to see if it is present in the data analysis without using that information when actually building the various types of models. So the data set that we have here comes from, it is part of our tutorial exercise called Stress in Poplar Trees. It is based on a study of genetically modified poplar plants by GCMS metabolomics, and every column here is a GCMS column with a either identified metabolite or something that is not identified. In this study we have a wild type consisting of 10 samples, and we have a modification consisting of 9 samples. And in the original article there were actually 2 modifications that were investigated together with the wild type. It was an up regulation and a down regulation within a certain gene that is involved in the production of pectyl methylesterase, and this is an enzyme that deesterifies methylated groups within the pectin. In this example we will compare the wild type with the up-regulated samples, and they have the notation 2b. So once we have imported the data and we look in the issues pane and it says no problems, we can finish the import, and we just have to give a name like that. And now we are going into the SIMCA software with the Omics skin turned on. If you don't see the Omics skin, we can go to the View tab under the Skins group, and that is where you can switch between the different skins. So we have a default skin, we have the Omics skin, and we have a spectroscopy skin. And for those of you that have an interest in the spectroscopy skin, you can look up at our website under the heading Recorded Webinars. There is then a recorded webinar on the spectroscopic skin that was made 48 hours ago. So in this presentation we zoom in on the Omics skin. So we have then imported the data. Sorry, we don't have to import another data set. We have already imported the data here. We can, if we want to, plot spectra, and then we will see in this case 19 curves or line plots in the same plot, and we can plot some of these lines individually if we prefer to. We will now launch the Omics Skins Analysis Wizard. That is done by clicking on the Analysis Wizard button. And then we have to tell what type of data we're working with. As I said, the skin and the analysis wizard comes with a pre-configuration of being able to identify 5 different types of data, and there is also a connected default scaling for each data type. This is mass spectrometry data. We are telling from which data set that we have imported to pull out the data. We could, as I said, import multiple data sets if we want to. We want to do both raw data analysis and the two-group comparison. We assign the wild type as the reference group. It has 10 samples, and we are assigned the treated group, the 2B group, the upregulated group, as group 1. We then click next, and then we are at the stage where we can do the raw data analysis. In the right-hand part of this window, we see the first variable plotted, and the color coding then comes from the class identity. We can then, using arrow keys, I'm now using up and down arrow keys on my keyboard, very quickly browse through the individual variables if we want to. In the left-hand part of this window, we see all the 80 variables or so plotted, and there are then for every variable 19 bars because there are 19 samples. I can then also here highlight a certain variable and zoom in on it on the right-hand side. It's just highlighting and then zooming in. If there is some anomaly in a certain variable, we can exclude that variable. We can also access a transformation toolbox where we can take, let's say, a logarithmic transformation or something else to transform the data. In this case, we will not go into that because there isn't that great need or anything to win by doing a transformation in this example. We click next, and then we come to the stage where the first data analytics model is calculated, and that is the PCA model. So every point now in the score plot is one sample, and you can see from the labeling which sample belong to the wild type and which samples belong to the upregulated group. We can see that in total the model has 5 principal components, and of the 5 components we explain 85% of the variability in the GCMS data. We can use the little tool up here to change what score vectors are plotted on the axis. We can, for instance, want to plot the third principal component scores together with the first principal component scores, and then all of a sudden we see that already in the PCA model there seems to be some separation between the wild type and the upregulated class. On the right hand side we have the DMOD-X plot, and the DMOD-X plot comes with a control parameter called the critical distance. It's symbolized here by the red dashed line, and that is a way to define an envelope around data points, a border of the model. And samples that have a DMOD-X value exceeding the critical distance are potential outliers and can be investigated, for instance, through a contribution plot. I just double-clicked on that sample, and then the contribution plot is opened up, pointing to the variables that have a large deviation for this sample. Now in this case the deviation for wild type sample number 10 isn't that dramatic. We start to get concerned when the DMOD-X value exceeds the critical distance by a factor of 2, 3, or maybe up to 5 or so. So in this case the conclusion is we have good in data and we can proceed to the next stage. And the next stage means that the OPLSDA model is calculated, and again we're displaying the score plot and the DMOD-X plot side by side. And in the lower left-hand part of this window we have all these model performance indicators. We have the explained variance, we have the predicted variance coming out of cross-validation, we have 2 similar measures coming from the response permutation test that I will show you. We have a p-value coming out of an analysis of variance on the cross-validation residuals called CV ANOVA, and we see that the model has 2 components, 1 predictive component and 1 orthogonal component. We can, in a similar way to the PCA model, we can investigate also in this model if there are outliers, in this case we have no outliers. There are no indications of deviations, and we can see that we have a good separation. We have all the wild type samples to the left in the score plot and all the upregulated samples to the right. So it means that there is information in the GCMS data that can indeed be used to separate the wild type from the upregulated group. Now, if we want to find out which of these variables have this discriminatory power, we proceed to the next stage, and then we see the S-plot. The S-plot is co-charted with what is called a ROC plot, and I will start with the ROC plot. ROC is an acronym for Receiver Operating Characteristic. The ROC plot is a visualization of the performance of a binary classifier. We have a binary classifier because we are trying to separate two groups of data from each other. And with the ROC plot comes also something called the AUC, area under the curve. The ROC plot is based on plotting for various thresholds of the classifying parameter in the model, the false positive rate together with the true positive rate. And for a good classifier, you will then obtain a graph like this, a curve that has an arcing towards the top left-hand corner of the plot at the combination 0 false predictive rate and 1 in true predictive rate. So the closer this red line is arcing towards the upper left-hand corner, the better is the performance of this binary classifier. Using a slightly different notation, you can also say that this red line is arcing towards the corner where you have 100% sensitivity and 100% specificity. Now I will look into this area under the curve. For a perfect classifier, the area under the curve will be 1.0. For a classifier with a random classifying performance, this red curve will coincide with the dashed diagonal, and the dashed diagonal would then have an area under the curve being 0.5. So effectively it means that for a normal functioning ROC curve or binary classifier, the area under the curve for the ROC curve will range between 0.5 and 1.0. So now we will look into the S-plot that I said during the PowerPoint part was based on plotting the correlation scale loading of the predicted component against the normal loading of that predicted component. Here we can highlight an individual variable and look at the dot plot, for instance, to resolve in the raw data what it looks like. We can also use, for instance, cutoff values. If we want to highlight all variables with a correlation loading larger than 0.5, we can use that tool there, and then all those variables that fulfill that demand are highlighted and here shown by the red color. Then we can also drill down to the raw data for these currently highlighted variables by using something called the descriptive statistics. And the descriptive statistics is a table that provides 8 univariate statistical measures of the currently selected 25 or so parameters. We can follow up on that also outside the analysis wizard. Alternatively, if we have no highlights, no markings, the descriptive statistics will describe the univariate statistics for all the variables in the data set. And you can also specify cutoffs in the loading. You do not have to specify cutoffs in the correlation scale loading, and you can combine them too. Provided you have this little tick box checked, create report, when we click finish, because this is the last stage in the analysis wizard, when we click finish, we will open up a report. And if you have been following other complementary webinars or our trainings or have used our softwares for some time, you will recognize this type of report graphical user interface. All our softwares contain generate report functionalities, and they will then give rise to an HTML-based document that can be saved and open up in any normal word processor. every report is based on a template, and the template consists of a number of placeholders, and the placeholder is something that is encoding a certain element that will go into the report. The placeholder can encode a certain plot, a certain table. It can also encode boilerplate text that is extracted from our documentation in our user guides and then put into the report. And you can start to experiment with these placeholders, change their order and add other placeholders, and in that way modify the report template to become your preferred report template. But we have other webinars on that certain topic. So I will here now close this report and I will not save any changes. Now, meanwhile, in the background, these models have been calculated, and when we exit the analysis wizard of the Omics skin, this is the view that we will see. We will have 4 overview plots tiled side by side. We have the score plot that we have looked at, and we have the Demolex plot that we have also seen inside the analysis wizard. But we have seen it not as a line plot, but as a column plot. This is the sort of Demolex plot we saw inside the analysis wizard, and by the way, it was also color-coded according to the class identifier information. So this was the sort of Demolex plot we were looking into. We can minimize that one. And then also among other plots is the explained variance and predicted variance for the Y variable. And here we have the loading, but the loadings are plotted as a scatter plot, slightly different representation. I will now take the opportunity and go through some of the tools that are available outside the analysis wizard. The plots here, those were the ones we just went through. The overview button will create those 4 plots that we just looked at that were arranged side by side. And then you can individually access also these tools. I will now zoom in under the validation group. Here we have the rock plot that we just looked at. We have the descriptive statistics that is also part of the analysis wizard. One tool that is summarized in the analysis wizard is the output of the response permutation test. It was called the validate in earlier versions of SIMCA. So what we are doing here is that we are creating between 20 and 1,000 permutations of the Y variables, and we are then calculating OPLS discriminant analysis between the original, in this case GCMS data, and randomly permuted Y data. And then we get intercepts from these regression lines, and these are the intercepts that are reported in the analysis wizard. The CV ANOVA is based on the ANOVA formalism, but instead of being based on the fitted residuals like in any normal regression analysis, it is based on the cross-validated residuals. So that is why it's called CV ANOVA, cross-validation ANOVA. And it is this p-value that is reported inside the analysis wizard in connection with the score plot of the OPLSDA model. In connection with this, I also want to take the opportunity to show you another tool that is called cross-validation scores. We can open up that score plot and tile it together with the normal score plot. So in the left-hand part we have the cross-validation score plot, and in the right-hand part we have the normal score plot, the score plot we saw in the analysis wizard. The cross-validation scores will indicate how sensitive the OPLSDA model is to the inclusion or exclusion of certain data points. Now here in this case we have an unlucky switch in the coloring that is not perhaps optimal, but we can use a highlight instead then. So if there is a sample that would have a dramatic change in its position between the original score plot and the cross-validation score plot, that would then indicate a sample to which the model is very sensitive. and you should exercise some care when looking into that sample and try to understand why does it have that sort of strong leverage on the model. On the other hand, if the score plot of the regular scores and the score plot of the CV scores are almost the same with very little shifting of the samples, then that is a strong indication that the model is devoid of influential observations, and it's very stable to the inclusion or exclusion of all the different observations. I will want to continue with this score plot a little. If we zoom in on the wild type, we will see that in the orthogonal component there is a little split among the samples. We have 4 samples down here, and then we have 4 samples in the wild type group up here. I can make a group-to-group contribution plot to see what are the differences between the currently blue marked wild type samples and the currently red marked wild type samples. Why do we have the split in the orthogonal component? We can then also size sort this one, for instance, and then from left to right we see how the different variables contribute to the split in the wild type group. This is a split, the systematic variation in the wild type group that is not related to the analysis question of separating wild type from the treatment class. And we can see that some of the samples that have the largest influence is glucose, sucrose, and fructose. They are all sugars, and for people that are initiated with the current type of experimental setup and the current type of samples, that would point to sample preparation issues. So the interpretation is that there might be a sample preparation issue causing the split in the wild type group, and being able to visualize that sort of systematic shift means we now have something to watch out for in the future if we would like to conduct similar experiments in another experimental campaign. If we can figure out exactly what we did and maybe try to remove that sort of those sort of actions, we can in the long term hopefully fine-tune our experimental procedures and remove that sort of behavior. Now the final thing I wanted to show you is also the existence and the results from the alternative group of samples, the down-regulated samples. And like a good chef, I have then prepared another example where we have run 2 models, not just one. The top model is the one we just looked at, that we did in terms of the analysis wizard. And in the lower part, we have the alternative model where we're comparing the wild type with the down-regulated group of samples, which is called L5. So here I have arranged 2 S-plots and 2 score plots. And the 2 upper plots are the ones we have just done together in the analysis wizard, and the lower 2 plots are the corresponding plots coming out from the comparison of the wild type with the down-regulated samples. And we can see that we have a good group separation also in this second case. I will now minimize these 2 score plots and use these 2 OPLSDA models to visualize another type of S-plot that comes inside the omics skin, and that is the so-called SUS plot. And I will do that for these 2 models, M2 and M4, and then try to arrange the SUS plot together with these 2 S-plots. By the way, SUS is shared and unique structures. SUS, shared and unique structures. So the SUS plot is based on taking, in the S-plots, we are taking out the vertical scale of that plot and also the vertical scale of that plot. And the SUS plot is created by taking these 2 vertical vectors and plotting them together. So here we have the correlation scale loading for the first 2-class model, where we compare the treatment group with the where we compare the wild type with the upregulated samples. And here we have the correlation scale loading for the other two-class comparison model comparing the reference group, the wild type group, with the down-regulated samples. Now, any variable ending up on the diagonal running from the lower left-hand part to the upper right-hand part is part of the shared structure. It is a variable that changes in the same way in both models. So for instance, this phosphoric acid is part of the shared structure. It is numerically higher in both the upregulated and the downregulated samples compared with the wild type. And the variable down here, for instance, cholesterol, is also part of the shared structure. This is a parameter that is numerically always higher in the wild type, regardless of whether you compare the wild type with the upregulated group or the downregulated group. So all variables here on that diagonal are part of the shared structure. Then on the axis, for instance, if we take inositol, we have what is unique. Inositol is a parameter that is changing a lot numerically when we are going from the wild type to the upregulated group of samples, where it doesn't change to any appreciable extent when we are comparing the wild type with the down-regulated samples. And in a similar way, glucaric acid is a parameter that changes a lot numerically, becomes larger numerically when we go from the wild type class to the down-regulated class, whereas it doesn't change at all when we're comparing the wild type with the upregulated class. So these are all variables that are far away from the origin and lying on the axis of the Seuss plot. They are part of the unique structures.
So with this little demonstration in mind, we are now moving over to the conclusion part. And we can say that the reason why we have developed this omics skin is that we would like to simplify the use of multivariate data analysis of omics data for people that have an interest in identifying potential biomarkers that can separate their groups that they are analyzing. And the skin with its core component, the analysis wizard, ensures that the scaling and plots in the SIMCA software are suitably tailored for omics data. As we've also seen, we have this report tool with its omics-specific templates that will facilitate documentation and not to forget, communication of the results coming out of the PCA and OP-LSDA models. We have more documentation on the SIMCA software and the omics skin and all the other skins. And if you would like to have that access to that information, please visit this URL address. Trying to summarize, we can say that one of the characteristic properties of the Umetrics Suite is that it will help you to see what others don't. And as I mentioned in the introductory comments, the Umetrics Suite comprises 6 software components: the model software, the easy analytics software, SIMCA Offline, the flagship, SIMCA Online, Control Advisor, and the active dashboard. And removing the names of the different software solutions, we can say that what you can accomplish with the Umetrics Suite of data analytics solutions is a very informed answer to all the critical questions that you're normally asking to your data. And the questions that we're thinking to or referring to here are the descriptive, diagnostic, and predictive and prescriptive questions that are summarized by the Gartner report. The descriptive question means that you are looking into answers such as what has happened. You would like to analyze your historical data and figure out what happened in the past and why it happened. The diagnostic twist of this reactive question is to find out why a certain thing happened. Two of these questions are more proactive in character rather than reactive, and the proactive questions are the predictive and prescriptive questions. The predictive one is that you would like to know what could happen in the future. And then we have the prescriptive question, where you try to use optimization and simulation algorithms to understand what should we do to make a certain outcome be true, or perhaps even more importantly, how should we act in order to avoid a certain issue to happen. So, with all this information and demo in mind, I would like to conclude by saying that what we would like to do from the Sartorius Stedham Data Analytics side is to help our users that are using the Umetrics Suite and analyzing their historical data to find the golden nuggets in the data. Also to find out not only what was important in the past, but also figure out how to plan future measurement campaigns in order to improve the situation, uh, to understand how to change a little and thereby grow a lot. And with those words, I would like to thank you all for your time and attention. Thank you very much.